Hello everyone, this is Acids and Bases Made Simple with Ms. Rodriguez, and today we're going over everything you need to know about the Acids and Bases unit in high school chemistry. So today we're going over acids versus base properties, calculating pH, and neutralization reactions. First, let's go over the definitions. A base is going to contain hydroxide, which is OH with a -1 charge. It's a proton acceptor. And when you hear the word alkaline, it's the same thing as saying that something is basic. Acids are going to contain hydronium, which is H with a +1 charge, and acids are proton donors. Another way to see hydronium is H3O with a +1 charge. BAD or BAAD is an acronym that helps you identify if a compound is an acid or a base. It stands for bases accept protons, acids donate protons. As for their properties, bases are going to taste bitter, feel slippery, they turn litmus paper blue, and they have more OH ions than H ions. Acids are going to taste sour, they turn litmus paper red, and they have more H ions than OH ions. So take note that solutions can have both OH negative ions and H plus ions. What determines if it's going to be basic or acidic is which of those ions it has more of. So if it has more hydroxide, it's basic. If it has more hydronium, it's acidic. And if they're perfectly even, then your solution is neutral. Conjugate acid-base pairs. So when you have a reaction and you put an acid and a base together, on the other side of the reaction, you end up with the conjugate base and the conjugate acid. In this case, the HF is our acid, and once the H plus is removed, so remember acids are donors, then you're left with F with a -1 charge, which is your conjugate base. That means that H2O is our base, and once it accepts a proton, so bases are proton acceptors, then you get your conjugate acid, which is the H3O plus. When we're naming acids and bases, we have to follow the IUPAC rules. When we name bases, your metal stays the same, and you always drop the end and replace it with hydroxide. When we're naming acids, there's a couple different ways to do it. It just depends on what the name should have ended with. So for example, if it should have ended in sulfide to name the acid, then you take hydro, insert the root, ic, acid. So for example, sulfide would become hydrosulfic acid. If it should have ended in ite, so sulfite, then you plug in the root, us, acid. So sulfus acid. If it should have ended in ate, then you take the root, you end it with ic, acid. So sulfate would become sulfic acid. When you call an acid or a base strong, what it means by strong is that it's going to have a very high pH for bases or a very low pH for acids. Out of all of the acids and bases out there in the world, there are only 8 that are considered strong bases, which are shown here. And there are only 7 that are considered strong acids, which is also shown here. So if you see an acid or a base and they're not on this list, then they must be either a weak acid or a weak base. The 8 strong bases are LiOH, NaOH, KOH, RbOH, CSOH, CaOH2, SrOH2, BaOH2. The 7 strong acids are HCl, HBr, HI, H2SO4, HNO3, HClO4, and HClO3. And again, if you see an acid or a base and they're not on either of these lists, then they must be weak. This is the pH scale. Notice how you have acidic on the left, basic on the right, and right in the middle is neutral. So 7 is a neutral pH. Anything less than 7 is acidic, anything more than 7 is basic, and the closer you get to 0, the stronger the acid. The closer you get to 14, the stronger the base. There are multiple formulas that we can use to figure out pH and pOH and H plus and OH negative concentrations. The first is pH plus pOH equals 14. The second is Kw, which is the water constant, which is equal to 1 times 10 to the power of negative 14, is equal to H plus times OH minus. And again, less than 7 pH, acidic, equal to 7, neutral, greater than 7, basic. Let's look at a couple practice problems. So first, we have the pH of orange juice is 4.11. What is the pOH? So using our first formula, we know that pH plus pOH has to equal 14. So to figure out the pOH, we just subtract from 14. So 14 minus 4.11 gives us 9.89, which is our pOH. Our second example, Dr. Pepper has an H plus concentration of 1.4 times 10 to the negative 5 molar. What is the OH negative? So using that second equation, we can plug in our H plus. We have to get OH, which is what we're missing, on its own. So we have to move the H plus over. We do this by dividing. So 1 times 10 to the negative 14 divided by our 1.4 times 10 to the negative 5, and that gives us our OH negative concentration, which is 7.2 times 10 to the negative 10. You can also go from H plus to pH and OH negative to pOH using your negative logs. So pH equals negative log of H plus, and pOH equals negative log of OH minus. So for example, what is the pH and pOH when there is 0.02 molar of HCl? So since we know the molarity of HCl, we know the H plus concentration. So we plug it into our formula. So negative log of 0.02, which is our molarity. So we're going to plug that in our calculator and we get 1.7. To get the pOH, we subtract from 14, so 14 minus 1.7 gives us a pOH of 12.3. If we're given OH, so for example, if there's 0.005 molar of NaOH, so now we know the OH concentration, we plug it into our formula. pOH equals negative log of 0.005. We put that in our calculator and we get 2.3. To get the pH, we subtract from 14, so 14 minus 2.3 gives us 11.7. And vice versa. We could also figure out the H plus and the OH concentration if we know the pH and the pOH. You do this by plugging it into these formulas. H plus equals 10 to the power of negative pH, and OH negative is equal to 10 to the power of negative pOH. For our examples, lemon juice has a pH of 2.9. What is the H plus and the OH negative concentrations? We know the pH, so we can plug it into our formula. So H plus equals 10 to the power of negative 2.9. Notice that the pH has a negative in front of it. We plug it into our calculator and we get 1.26 times 10 to the negative 3 molar. Since we know the H plus now, we can figure out the OH negative by taking that Kw formula and dividing by what we know. So Kw equals 1 times 10 to the negative 14 divided by our H plus, which is 1.26 times 10 to the negative 3, and we get our OH minus concentration, which is equal to 7.9 times 10 to the negative 12. We do the same thing for the ammonia, which has a pOH of 2.4, but this time we have a pOH, so we can figure out the OH negative. We plug in what we know, so OH negative equals 10 to the power of negative 2.4. Plug that into our calculator, and we get 3.98 times 10 to the negative 3 molar. Since we know the OH negative, we can figure out the H plus by dividing by Kw. So Kw equals 1 times 10 to the negative 14 divided by our OH negative, which is 3.98 times 10 to the negative 3. Plug that in our calculator and we get H plus, which is 2.5 times 10 to the negative 12 molar. Neutralization reactions. When you combine an acid with a base, they end up neutralizing each other and forms water and a salt. So for example, here we have a double replacement reaction, so NaOH plus HCl, and on the other side you have NaCl and H2O. Notice that after the double replacement happens, so double replacement means both of the compounds are going to exchange partners, you end up with H2O, which is water, and what's left over is the Na and the Cl, which forms sodium chloride, which is a salt. In a titration, a neutralization reaction occurs, and it uses a known concentration to figure out an unknown concentration of an acid or a base. So here we have the neutralization reaction of 3KOH plus H3PO4 makes K3PO4 plus 3 H2Os. So KOH is our base, and we know that we have 20 milliliters of 2 molar KOH. H3PO4 is our acid, and we know we have 25 milliliters of it, but we don't know the concentration of it. To do this, we have to perform a titration calculation, which is a 3-step process. Step 1, we use the formula, molarity equals moles over liter, and we plug in the information that we know. So we know all of the information for KOH, so we're going to plug that information into the formula. So 2 molar equals X, because we don't know the moles, over 0.02 liters. Notice that the 20 milliliters, we had to turn it into liter first before plugging it into our formula. We did this by moving the decimal 3 times. So instead of plugging in 20 milliliters, we plugged in 0.02 liters. To solve for moles, we have to move the 0.02, and we do this by multiplying. So 0.02 times 2 gives us 0.04, which is our moles of KOH. Now that we have moles of KOH, we can turn it into moles of H3PO4 by using our mole-to-mole stoichiometry. You always start with what you know, so 0.04 moles of KOH. If we have moles of KOH on top, we want moles of KOH at the bottom. And looking at our formula, KOH has a coefficient of 3. So there are 3 moles of KOH for every 1 mole of H3PO4. We multiply our top number, divide by our bottom number, so 0.04 times 1 divided by 3 gives us 0.013 moles of H3PO4. Now that we have moles of H3PO4, we can figure out the molarity of H3PO4 by plugging it into that molarity formula again. So molarity equals moles, which is 0.013, over liters. So again, we turn the 25 milliliters into liters, which is 0.025 liters. We plug that in our calculator and we get 0.53 molar of our H3PO4. So the reason why we perform the titration calculation is because we're trying to find the equivalence point. So in a titration, you have your analyte and you have your titrant. The analyte is whatever solution you're starting with. So in this example, there's a strong acid that we're using as our analyte. And you use the opposite as your titrant. So in this case, we have a strong base, and you slowly drip your titrant into your analyte to try to reach that equivalence point. And the equivalence point is always where the solution inside your beaker becomes neutral. So when the pH reaches 7. Notice that there is a very slow increase in our pH as you add that titrant, and then it becomes a very steep slope as we approach the equivalence point. Once you get past the equivalence point, then the slope slows down again. And using the titration calculations that we did on the last slide, it can help you find that equivalence point by telling you the molarity and the volume that you need in order to make your solution neutral. All right, that is everything you need to know about the acids and bases unit for high school chemistry. Thank you so much for your time. Let me know if you have any questions in the comments below. If you found this video helpful, make sure you hit that like button and subscribe so you don't miss any of my future chemistry content. If you're a chemistry teacher and you would like access to this exact PowerPoint, it is on my TPT store called Chemistry Made Simple, as well as worksheets, labs, and activities that align with this unit and all other units of high school chemistry. I hope you have a great day. Bye!